to my YouTube channel, Usano-Goldie RL Marquez. This is Integral Calculus, Basic Integration, Section 1.2, General Power Formula for Integration. In this video, I will be discussing more examples of indefinite integrals which can be handled by the general power formula for integration. Recall the following basic integration formula: general power formula for integration, or GPF. In the integral u to the n du, u to the n is the power function not equal to a constant. N is the exponent, which is a constant different from -1. U is the base, which is a function other than a constant. And du is the differential of the base u. If all of these things are satisfied, this integral of u to the n du is equal to u to the n plus 1 all over n plus 1 plus c. Remember, n not equal to -1. Example 1.2.9. Evaluate the integral of 4e to the 3x plus secant 3x tangent 3x quantity dx all over 4th root of 4e to the 3x plus secant 3x. Let us express this integral in the form of integral of u to the n du. So we have 4e to the 3x plus secant 3x quantity to the -1/4 times 4e to the 3x plus secant 3x tangent 3x quantity dx. Let u be equal to 4e to the 3x plus secant 3x with n equals -1/4. The differential of the u is equal to 4 times e to the 3x times the derivative of 3x is 3, getting 12e to the 3x. Derivative of secant 3x is equal to 3 secant 3x tangent 3x multiplied to dx. So the differential of u is 12e to the 3x plus 3 secant 3x tangent 3x quantity dx. Factoring out 3, we get 4e to the 3x plus secant 3x tangent 3x inside this parenthesis multiplied to dx. So let's check if the differential of u is satisfied with u equals 4e to the 3x plus secant 3x. So notice that there is a missing factor 3. So let us supply that and then balance outside by 1/3. So multiply by 3, balance by 1/3 outside the integral. So we now get u to the n du. Since this integral takes the form of integral of u to the n du, hence it is equal to u to the n plus 1. N plus 1 is 3/4. So all over 3/4 times 1/3 plus c. So simplifying, we get 4 over 9 times 4e to the 3x plus secant 3x quantity to the 3/4 plus c. So this is the integral of the given problem. Example 1.2.11. Evaluate the integral of e to the 40 secant cube of e to the 40 tangent of e to the 40 dt. So here, the possible u to the n is secant cube of e to the 40 or secant e to the 40 quantity cubed times e to the 40 tangent of e to the 40 dt. taking u as secant of e to the 40 and n equals 3, the differential of u is equal to 4 e to the 40 secant of e to the 40 tangent e to the 40 dt. But notice that this e to the 40 tangent e to the 40 has a missing quantity for secant of e to the 40. So let's get this secant of e to the 40 from secant of e to the 40 quantity cubed. Hence, we have secant of e to the 40 multiplied by e to the 40 secant of e to the 40 tangent e to the 40 dt. Now, the exponent is 2 and not anymore 3. So, but if you're going to check the differential of u, there is another missing factor, that is 4. Since it's a constant, we can supply that and then balance outside by 1/4. So this integral now takes the form of u to the n du. So since this is equal now to the integral of u to the n du, so it is equal to u to the n plus 1 all over n plus 1 times 1/4. So getting 1/4 times secant of e to the 40 quantity cubed over 3. Simplifying, we have 1 over 12 secant cube of e to the 40 plus c. So this is the integral. Example 1.2.12. Evaluate the integral of tangent x times tangent inverse of log of cosine x to the base 5 all over 1 plus log of cosine x to the base 5 quantity squared dx. So here, the possible u is tangent inverse log of cosine to the base 5. And the possible differential of u is tangent x over 1 plus log to the base 5 cosine x quantity squared. U is tangent inverse of log to the base 5 of cosine x, n is equal to 1. The differential of inverse tangent of log to the base 5 of cosine x is equal to negative sine x over cosine x times ln 5 times 1 over 1 plus log to the base 5 of cosine x quantity squared dx. So let us simplify this. Sine over cosine is tangent x. So we have negative tangent x dx all over 1 plus log to the base 5 cosine x quantity squared times ln 5. Now let's check the differential of u. So the differential of u, in the differential of u we need negative in the numerator and ln 5 in the denominator. So let's supply that. So we get negative tangent of x dx all over 1 plus log to the base 5 cosine x quantity squared multiplied to ln 5. But since we multiply this integrand by negative 1 over ln 5, we have to compensate that outside the integral. So multiply outside by negative ln 5, which is the reciprocal of negative 1 over ln 5. So the integral now takes the form of u to the n du. So hence, we have u to the n plus 1 all over n plus 1 times negative ln 5 plus c. Hence, we have negative ln 5 over 2 times tangent inverse of log to the base 5 cosine x quantity squared plus c. Example 1.2.13. Evaluate the integral of 3 to the hyperbolic tangent x squared times x hyperbolic secant squared x squared dx all over 1 plus 3 to the tangent h of x squared quantity to the 2/3. Let us express this integral in the form of integral of u to the n du. This denominator is the possible u to the n. When we bring it up, it is to the negative 2/3. Hence, we have 1 plus 3 to the hyperbolic tangent of x squared quantity to the negative 2/3 times 3 to the hyperbolic tangent of x squared x times hyperbolic secant squared x squared dx. Let u be equal to 1 plus 3 to the hyperbolic tangent of x squared with n equals negative 2/3. Du is equal to derivative of 1 is 0, derivative of 3 to the hyperbolic tangent of x squared is 3 to the hyperbolic tangent of x squared ln 3 times 2x hyperbolic secant squared x squared dx. So this is also equal to 3 to the hyperbolic tangent of x squared 2x ln 3 hyperbolic secant squared x squared dx. So checking for its possible du, so there is a missing constant factor 2 ln 3. So let us supply such. So we have 2 ln 3 multiplied inside, balanced outside by its reciprocal 1 over 2 ln 3. So this integral now takes the form of u to the n du. So hence we have 1 over 2 ln 3 times u to the n plus 1. N plus 1 is 1/3. So we have the 1/3 over 1/3. So simplifying, we get 3 over 2 ln 3 times 1 plus 3 to the hyperbolic tangent x squared quantity to the 1/3 plus c. So this is the integral. Or negative ln 5 over 2 arctan squared of log to the base 5 cosine x plus c. So this is the integral. Example 1.2.14. Evaluate the integral of cube root of arc secant squared of 2 ln x dx over x ln x square root of 4 ln squared x minus 1. Let us express this integral in the form of integral of u to the n du. So this cube root of arc secant squared 2 ln x is possible to be u to the n. So we have arc secant of 2 to the ln x quantity to the 2/3 times dx over x ln x square root of 4 ln squared x minus 1. So let u be equal to arc secant of 2 ln x n 2/3. Its du is derivative of 2 ln x 2 over x. For arc secant, we have 1 over 2 ln x square root of 2 ln x, that is 4 ln squared x minus 1 times dx. Simplifying, we get du equals dx over x ln x is square root of 4 ln squared x minus 1, which is exactly this differential. Hence, we have integral of u to the n du. So this is equal to u to the n plus 1, but n plus 1 is 5 over 3. So we have arc secant of 2 ln x to the 5 over 3 over 5 over 3 plus c. So we have 3 over 5 arcsecant of 2 ln x quantity to the 5 over 3 plus c. So this is the integral. That's all for now. Thank you for watching. Please don't forget to subscribe to my YouTube channel, Usano-Goldie RL Marquez. Bye.